Okay, here's a quick peek at Math 3 Unit 6 Worksheet 2, Proving Number Patterns. And I've taken a couple of the problems off of this worksheet and copied them over onto lined paper just to make myself a tiny bit more legible. For these proving number patterns, students are going to want to make the directions say verify each number pattern is correct, so they should actually try the math. Let's see, 3 times 1 is 3, plus 1 is 4, 2 squared is 4, yep, that works. 15 plus 1 is 16, 4 squared is 16, yep, that works. They want to try that and make sure it's right. If it appears to be true, express the number pattern using variables and then prove that it's always true. So that's what's going on with these. Express using variables is kind of challenging to them. So this is what I would tell you to do to train them to express using variables. The first thing you want to do is see, are there any numbers in here who are never changing? And as I look at this pattern, this 1 is never changing. So that 1 is going to be in my variable expression. I'm going to have a 1. But every other number is changing some. And so you want to see the relationships between those numbers. Here I see that 1 and 3 are like 2 apart. Everything's 2 apart here. It's like it skipped over a number. And the number, whatever it was it skipped over, is over there. And so I decided to make this first column n. And as I did that, let me change color so that shows up a little bit better. As I did that, if I make this n, this first one will be n times, and this next one is 2 bigger. It's not n plus 1, it's n plus 2. And then the 1 never changes, it's plus 1 every time. And then this one, remember, went right in between there, and it was n plus 1 squared. And so they're going to be trying to express these with variables. That is a talent that we would like to develop in them, to be able to get variable expression for the patterns that they observe in things. So now as they simplify, they're going to see that this is true. We have advanced math to get them to be formal provers, and so I would encourage you to let them work on both sides, but don't let them add over from one side to the other. They want to show that this side is the same as this side, without assuming the equality that adding things to both sides and multiplying things by both sides assumes. So, but let them work both sides. Don't feel like they have to completely do it like they would a trigonometric proof or a formal proof. So I'm going to multiply this n squared plus 2n, and then I also have that 1 right there. There's no like terms I can combine anymore there. Some students might think of factoring. If they did, they would be done. But my question is this really equal? And so over here, I'm going to do n plus 1 times n plus 1. And when I multiply that out, I will get n squared plus 2n plus 1. And then when I look over here, I have n squared plus 2n plus 1. And so when I see that those are equal, I usually have my kids put a check. Yes, they really are equal, to show that they just didn't get tired and quit and not notice that they were equal. You could have them put happy faces or bubble around it or whatever it is that you want to have them do. So it would be okay with me if instead of doing this side had been factored and it equaled that. Would not be okay with me if they subtracted 1 from both sides, if they subtracted n squared from both sides, and they eventually got 0 equals 0. I'd like them to leave all the work on one side, on that side. When you add 1 or subtract 1 from both sides, you're assuming equality, because it's the addition, subtraction property of equality that you're using to do that. Since you don't know they're equal, you don't want to assume that equality, and so you just simplify like it's an expression on one side, not crossing that barrier when you don't know that they're equal. So that's what's going on with that. There's several like that. Here you can see number 2 has cubing. That's a lot of then practice multiplying out n plus 1 times n plus 1 times n plus 1. Here's to the 4th power, but I just had that be n to the 4th, and so I didn't have such a big challenge on that one. Here's one on the next page that has some fractions, which allows us a chance for rational function work. I don't see any number that is staying unchanged in this, so every single thing is going to need a variable. I thought that I would just make this n and this one n plus 1. When I did it, my students, a lot of them wanted to make this n plus 1 and this n plus 2 because neither of them were n. And so it's your choice, but I chose to make this n. The proof will work either way. It is true that 1 is on the top of every fraction, so if I make this 1 over n, then this is 1 over n plus 1. Notice that my students did this, 1 over n plus 1 minus 1 over n plus 2. Both of those will work. And this, if you look at the pattern, 2 times 3 is 6, 3 times 4 is 12, 4 times 5 is 20. It appears they're multiplying those, so they're getting 1 over n times n plus 1. My students had this pattern, n plus 1 times n plus 2. Both of these will work. Okay. So in terms of simplifying, I will get a common denominator here. So that means this first fraction I'm going to multiply by n plus 1 on the top and the bottom. And the second fraction I'm going to multiply by n on the top and bottom. So in this first one I'll have n plus 1 over n times n plus 1 minus, and on this next one I'll have n over n times n plus 1. And I'm hoping, but I'm not really sure they're equal yet, that it comes out to this. So students might wonder, why am I not multiplying through to clear the fractions? I'm not multiplying through to clear the fractions because I don't know they're equal, so I don't have equality, I don't have properties of equality there. So now that they have a common denominator, I can put that all on one fraction. And the n's will cancel out, and I'll have 1 over n times n plus 1, which is exactly what I have over here on this side. So that does work out. And sometimes I make a big deal about have some kind of celebration, so I know you didn't just get tired and not notice that this equaled that. Make a happy face, make a yippee, write yippee, give confetti, whatever I play with my students and let them celebrate. So sometimes they'll put balloons and all kinds of different things to show me that they realize that they got to a spot where the two things are equal. Okay. Just to show you one or two others without having to work through them really quick. There was this one. I had to multiply out and get n to the fourths as I did this work. And there was this one. It was another one very similar to the one I just did. I just did this one with you, and I had to get a common denominator, and then eventually they came out equal. And so again, nice algebra practice, which they need. So that's a good thing about this lesson. All right, so just giving you an idea as you're choosing which parts of 6 to do, that's what this lesson does. If you didn't have as much time, you might just do 6-1 and 6-6, or 6-1, 6-5, and 6-6. But this is a nice, more algebra practice if you have the time. Thank you and good luck.